Welcome, everyone, to year 7 of the Trees Around the Globe Student Research Campaign. This webinar is the first webinar for year 7, and we're glad that GIO and the NASA Globe Program Office agreed to extend the campaign another year. So this, once again, is year 7. Today, we're going to kind of do a little bit of a review and then a little look ahead and what we want to do for this upcoming year 7 of the campaign. So we're going to talk a little bit about some essential NASA missions, and we're going to go over some things that it's the electromagnetic spectrum. And there's a reason we're going to do that, is because we want to talk about some of the ways the satellites that align to the globe observations of land cover, tree height, and other things related to globe protocols, how what we call the spectral signature of these satellites, how they work, meaning there are a single spectral band satellites, there are multi-spectral band satellites, and it sounds very technical and complicated, but you'll understand after a little bit, because I'm going to be talking about the ISAT-2 and GEDI missions. Peter Nelson, when he joins in, he's finishing something up right now. When he joins in, he's going to be talking about the multi-spectral with the Landsat series of satellites and the upcoming Landsat next. And then Peter Falcon will be talking about the NISAR mission and doing a quick introduction to a presentation we're going to have on that mission at next month's webinar. And we're finalizing that date right now with our scientist, who will be the lead presenter and feature presenter for next month. So let me go ahead and do a couple introductions here. Oh, once again, here we go. The Trees Around the Globe Student Research Campaign. This is year 7. Actually began on 1 October 2024, and we will be running through 30 September 2025. And I wanted to highlight some of these really cool quotes that I received in emails. And I see John Moore is on with us today from the Palmyra Cove Nature Park. He said, "Congratulations, it is an awesome work you are all doing. I'm proud to be a small part of it." John, you're a big part of it, of this, because you've been with us since the beginning. So thank you, John. Also, Ana Prieto from Globe Argentina. She says, "What great news. It is very good that this campaign continues. I personally have learned a lot in these years of campaigning. Thanks to this, we were able to organize a campaign in the Globe Latin America and Caribbean region, also known as the Globe LAC." And Larissa Shelkin from Global STEM Center USA said, "Congratulations. I'm so happy for you and your team. Thank you for your incredibly hard work and efforts. I look forward to continuing to work with you and everyone on this very important campaign." So thank you all. And there's other ones that we didn't get up on here due to space, but these webinars and this campaign couldn't be in existence without all of you. I know some of you are new, so we hope you stay with us for the duration. A lot of you have been with us for the duration since we began on the 15th of September in 2018, which was in conjunction with the launch of the ISAT-2 satellite, the Ice Cloud and Land Observation Satellite 2, or ISAT-2. And that has a huge, one of its objectives is to use lasers to measure the height of objects on Earth, including trees and forests around the world. So once again, thank you, and we're excited to begin year 7. And I thought in year 7, year 6, I did this. I put up some nice inspirational quotes here. Once to get people thinking, I decided to put 2 up here because I couldn't choose between the 2 because I like both of them. And I didn't want to save one till next month. But one is by an American author named Karen Joy Fowler. And she says, "Trees are as close to immortality as the rest of us ever come." Just thought that was an interesting quote, just something to ponder. And then another one from Nelson Henderson, who was an American councilman. "The true meaning of life is to plant trees under whose shade you do not expect to sit." So I really like that quote because that one really talks about that, we plant trees because we want them to grow large, want them to grow long, live long lives. I just really think that's a really cool quote because very ahead of his time, thinking about that and how we We want trees to exist because trees, as you know, trees are an indicator to climate change. I mean, back then, when this guy was in American Council, there wasn't a lot of talk, of course, about climate change because you really didn't have the technology to really measure it and understand it like we do today. We had scientists out there taking observations around the world in the field, but of course we didn't have anything close to any technology in space or in the air or anything, or the fancy technology like terrestrial laser scanners and things that we see in the field now. So I really enjoyed this quote here. So I wanted to put that one up as well. Enjoy those. All right, so today, and we have a lot of moving parts here, so that's why I threw our campaign team member names in here, so I could keep it all together because there's a lot going on. So this is a welcome to year 7 in the Trees on the Globe Stream Research Campaign. We're going to also talk about aligning to the 30 years of GLOBE, understanding the past, present, and the future. And then we're going to dive a little bit into the tour of the electromagnetic spectrum to try to just focus a little bit about what that is and then how it ties into the campaign. And you don't use much of the EM spectrum when you're talking about looking at the tree height from the ground. You're looking at land cover. You're doing these physical observations. But then when we're talking about
we are still working on that. So our vision is for the scholars to.
All right, no worries. So with the data that you can compare to the GLOBE data, a lot of that data comes from satellites, NASA satellites. We have the Landsat series, which is NASA and the United States Geological Survey. But in order to understand how these missions work and how we can compare the data to the GLOBE data, like tree height and land cover and green up, green down, things like that, we need to know a little bit how these satellites work, what they're looking at. And that's why we have on here, like I mentioned earlier, single spectral versus multi-spectral, and then talk a little bit about NISAR then. And then we're going to talk a little bit about, and this is close to John Moore's heart. So Peter is going to start off the presentation. It's kind of a interactive one where we're going to really talk about like the past, present, and future of looking at trees and land cover. Since we're focusing on that 30 years of GLOBE, we're really and the IVSS 2025 is really focusing on that 30 years of GLOBE data. We want to be able to understand what the past data means. We want to understand what the present data means, so we can then figure out what this future data is going to look like, what it's going to, basically what it's going to look like. So, there's a couple things here that we're going to go over, and we're just using this as an example. And John, we didn't say anything to you ahead about this. It's just kind of we're testing this out during this webinar. But an example, the Palmyra Cove Nature Parks Institute for Earth Observations in Palmyra, New Jersey. And that's where John Moore here is the lead of, and he is the manager of this nature park, this institute. And we're going to look at it in different ways. I have a couple slides I'm going to bring up of some things that tree height observations and things we've done there, and observations we've done, at different events at Palmyra Cove, and we'll go from there. And then we're going to have a little bit of a discussion towards the end. So what I'm going to do now quickly is I'm going to, let me do these first. Sorry, I forgot I had these again, but I don't know how I forget this because these are in every webinar. But these are the metrics for the major observations that are part of the campaign: tree height, land cover, green up, green down, or greenings. I want you to draw your attention to year 7. That's where we are now. And we already have 1,629 measurements from 673 global sites. We have over 900 tree height measurements, over 400 land cover, and 300 green up, green down observations. So, and as I always say, a little disclaimer, we know that all of these measurements are not coming from active Trees Around the Globe Student Research Campaign participants, but that is data that we want the educators and the students that are part of the campaign to really focus on, because that is really looking at the change over time. Even though this is just over 6 years of data and we're looking at 30 years of data, this is a great place to start. So with that said, for the whole life of the campaign so far, At the bottom here where it says total, we have 210,469 observations of tree height, land cover, green up, green down from over 66,100 global sites. So, thank you to everyone who has been doing this. Right now, we actually have an intensive observation period going on, and it's in conjunction with the North American Phenology Campaign and has ties to the European Phenology Campaign as well. So this is just September through December, where we're asking people around the world, primarily, I'm going to say in the Northern Hemisphere, because we're looking at the green down right now. We're seeing how that's changing over time. But then when we also have the folks in the Southern Hemisphere where we'd like that data as well, because of course you're in the green up phase right now. So we'd like to see that as well. So this data will go into support the data that the North American Phenology Campaign and the European Phenology Campaign are looking for. We had a Globe Observer Connect event last month that I was leading, but we also had speakers. We had Haley Wickline from the North American office in the North American Phenology Campaign, and we had Lenka Klager from Globe Czech Republic, but also from the European Phenology Campaign and the Globe Europe and Eurasia Program Office. So we had lots of great presenters from different parts of the world. So and Marcus, who is on here, Marcus, being an educator and being a Globe superstar, has done lots of this with greenings and land cover and investigations of, looking at a changing environment over time with his students in the classroom. So Marcus was there from Globe Switzerland to really, give that perspective of a teacher who's working with students and taking these observations and having them, learn more about their environment through these observations. So, we appreciate all that. And you can go to the Globe website or the Globe Observer website, observer.globe.gov, and type in the Globe Connect. Do Globe Connect. I believe that was it September? Geez, I can't remember, but just Globe Observer Connect, and it'll bring up, you can watch the video of that Globe Connect event. So I wanted to get a little bit of this because a lot of you are probably following the IVSS 2025, 30 Years of Globe, Understanding the Past, Present, and Future. So I just have this timeline up here. This is for you to, that's on the website. The URL is right there at the bottom. Sorry, it's a long one. I'll put it in the chat after I stop sharing here. I can't do it while I'm sharing, sorry, because my whole screen's filled up with this. But you can see that there was just recently an Accessing Data from the Globe Data website database webinar last week. The general IVSS webinar happened on the 16th of September. And the next one, there will be a badges webinar on the 4th of December, 2024. You can see it runs all the way through here. But one thing that's really important is that the period for submitting projects is 16 December of this year to 5 March of next year. So please keep that date in mind if you and your students are going to be submitting Globe IVSS 2025 student research projects. And then you can see there's a lot more happening after here as well in this timeline. So I just wanted to be aware of that. But the reason I show this is once again, our campaign this year, year 7, will have a big focus on 30 years of Globe and understanding the past, present, and future. So we're really going to focus on that data and a combination of that data because the Globe program with these projects really wants you to use the Globe database and use Globe data from around the world because, as you know, you may have seen it on the Globe website. When you're on the front page and you scroll down, it says how many observations are in the database, and it's well over 250 million observations are in the database right now. So there's a lot of data out there. So there's going to be different ways that, we know it's impossible to filter through that much data. So that's one of the things we're going to try to do with our campaign this year and the webinars is to, distill some of that data. So it's a little bit easier to work with. And of course, we're going to focus again on these online tools that really help you do comparisons. It's something also is welcome for the student research projects in addition to using the Globe database data for the last 30 years is to look at the NASA data that aligns to some of these observations that the students are looking at when they're looking at the GLOBE database, when they're getting that data from the GLOBE database. So, all right. Here's electromagnetic spectrum, okay? So you probably have seen something like this where it runs all the way from the radio waves all the way through gamma waves, and all of these things here, all of these different waves, the radio, microwave, infrared, ultraviolet, X-rays, gamma waves, okay? They all sit on the electromagnetic spectrum, and depending upon what we're looking at and what satellite we're using different things. Some of them, we're using microwave, like kind of radiation. Some of them were using the IR, infrared. Some of the satellites like ICED-2 were using visible light because we're using lasers in the green wavelength. Okay, so we wanted to showcase that because, a lot of times, Landsat is also, uses different bands, okay, of the visible light bands. But what's wild about that is because you've probably seen the Landsat imagery, of course, because Landsat imagery is gorgeous. We're taking pictures of the planet that get better and better and better with every Landsat mission that's out there. But then I often hear with ICED-2, can you send me a pretty picture of ICED-2 data of trees and or ice? Can you send me? I can't, because even though we're using that part of the visible spectrum, we're using lasers at 532 nanometers, which is green light. It is not like a camera. We're not using it in that sense, like Landsat is doing, with red, green, blue. We're not doing it that way. We're using the green laser pulses. So we're basically photon counting. So we're getting data in a totally different way. That is why right now we are still working on how to get some type of satellite match in Globe Observer for tree height. Because as you know, we have ones for cloud observations where if you do it during, around close to an overpass of one of the satellites, you'll get an email sent to you with your data and the data from one of the satellites, or one or more of the satellites. We love to be able to do that when you take tree height observations in a particular area to get the latest ICED-2 data, in an email. So we're working on that. It's just a lot more difficult because one is we're getting probably 1 to 2 terabytes of data a day from ICED-2, and there's something called a data latency, meaning that the data is coming in so much that the data gets processed in batches. So what that means is that the data comes in and it gets stored for a bit, and then it gets processed all at once. And then because if the computer is constantly running, it's going to eventually fall behind because of just that huge amount of data coming in. So it gets stored and then processed. So you'll see if you've ever gone to open altimetry, you may have seen that some of the data when you're in the calendar, today is the 15th of October. That if you go in there now, the latest data we have is from the end of July of this year. But if you would have gone in July, you would see that the data was still back from 2023. So it works in batches like that. So electromagnetic spectrum, here's this big old definition for it, but I'm going to read it because it'll bring us kind of down into the video I'm going to show you next. The electromagnetic, or EM spectrum, is the range of all types of electromagnetic radiation. Radiation is energy that travels and spreads out as it goes. The visible light that comes from a lamp in your house and the radio waves that come from a radio station are two types of electromagnetic radiation. The other types of electromagnetic radiation, or EM radiation, that make up the electromagnetic spectrum are microwaves, infrared light, ultraviolet light, X-rays, and gamma rays. It's kind of the overarching one. So in order to put that in the picture form, I'm going to show you this, and I'm going to say there's no sound to this, okay? So I'm just going to play it. It's only about, it's like 1 minute and 22 seconds long. So, but it shows you, it breaks down, because a lot of people, they hear gamma rays, are like, what is that? What are gamma rays used for, And so this is a really cool video that was put together that showcases what each one of these parts here of the electromagnetic spectrum, what are these types of radiation and what are they used for? There's radio waves. You should all be familiar with that. And microwaves. There we have infrared. Which is really good at showcasing heat signatures. There's optical or the visible, which is a lot of what we work with as well. There's ultraviolet. We also use a lot of ultraviolet energy to look into deep space. And you've all know of X-ray. And gamma rays. A lot of deep space applications for NASA with gamma rays, checking out the gamma ray radiation released by, distant stars and galaxies and clusters. All right, so that was just a little foray into that. So when we talk about the NASA missions that have something to do with trees and land cover and also the EM spectrum, we get a great variety of these. And, some of these we haven't talked about for a while, but a lot of these are ones that are used with some of the satellite matching for clouds. But then also we have ones that are really good at comparing to different things in the GLOBE program. We have GPM, Global Precipitation Measurement Mission. I'm sure many of you have heard of that. That's looking at precipitation. And we have Precipitation Protocol. We have Landsat. I have Landsat 9 there because that's the most recent one. So we have the Landsat 9 satellite. We have Soil Moisture Active Passive or SMAP mission. And I put that in here because we do have the SMAP block pattern soil moisture protocol, which Dixon Butler and I co-wrote many years ago to help measure volumetric soil moisture and be able to compare it to the SMAP satellite. Then we have ISAT-2, which I'll talk a little bit more later on. We have Calypso looking at clouds. We have Aqua, and that's looking at water, but it also gets some good land features as well. Terra, great land features. We're looking at they really a huge satellite for looking at change over time. We have the CloudSat mission, which Peter is very familiar with. He worked on that mission for many years. And then we have the GRACE mission, a gravity recovery and climate experiment follow-on. And if you don't know much about the GRACE mission, look it up. It's just a pretty amazing satellite. It's actually dual satellites that fly side by side and kind of bounce back and forth towards one another in measuring the gravity on the planet, the gravity of bodies of water and things like that, to see where changes, to identify where there might be hidden water under the Earth's surface that we didn't know about, hidden reservoirs and places like that, things like that. So very, very cool bunch of satellites. So we'll be focusing on a bunch of these satellites throughout year 7 because they do tie into, not every one of these measures trees, not every one of these gives land cover observations, but we need all these satellites together in order for us to paint not just a picture of what's happening in an area, but a global picture of how our planet's changing over time. So we have all these satellites like this just moving around the Earth. And I always get the question, and I think this is funny, I always get the question that from the younger students in elementary school, usually like the primary school, that these look so close. Don't they ever hit each other? And they don't. And as you know, as educators and scientists who are here and citizen scientists, that, space is a big place. Even though they look close together here, they are definitely far apart. But I show this because these are all Earth observing satellites and instruments. I believe the space station on this one, I think it is, but I'm not. Yeah, ISS. There it goes, right there around the North Pole right now. So ISS is on here because there's a bunch of instrumentation on it that is measuring it, including the GEDI mission instrument. So I'm going to quickly go into, oops, sorry, that cut off a little bit on the bottom, but I'm going to start off by talking a little bit about some of the satellites and, talking about the single spectral. And this is a single spectral band because we are using this single color, this single laser light. And it's different between GEDI and ISAT-2, but I'm going to showcase both of these here. So when we talk about single spectral bands, here we go, are regions of a given spectrum having a specific range of wavelengths or frequencies Most often, it refers to electromagnetic bands, regions of the electromagnetic spectrum, which you just saw in the video and you saw in the diagram that was there earlier. But we're mentioning GEDI and ICET2, of course, because both of these can measure tree height. GEDI, also known as the Global Ecosystem Dynamics Investigation, is an instrument on the International Space Station. It is not its own independent satellite. It is an instrument that is attached to the International Space Station, and it focuses just on measuring the height of tree forest canopies between 51.6 degrees north and 51.6 degrees south latitude. It only focuses on the forested areas. Conversely, we have ICET2, which is an independent satellite, meaning that it's orbiting around the Earth. Okay, it's called a near polar orbit, so it's going 88 degrees north, 80 degrees south as the Earth rotates. But it's ICET2 because its primary objective is to look at the changing height of ice sheets and sea ice at the North and South Pole and other areas too, like Alaska, a place like that. But because it's a laser altimeter in space, meaning that it has an instrument called an altimeter, which measures elevation, slope, things like that, but it's measuring height. It's looking at that third dimension, okay? It can also measure trees, so it measures tree heights as well. So with that said, I have these two, oops, sorry, should have gone too far, went too far. All right, there we go. So we have ICET2 and we have GEDI. They were launched pretty close to each other. Of course, ICET2 was a couple months before. And then on the 5th of December, 2018, they sent GEDI up to the International Space Station. As you can see here, what's interesting is that ICET2 fires off green lasers and GEDI fires red lasers. And the one is, I was talking to a scientist, an engineer recently, and I said, why are they using the green? And he said, it just is more efficient at the 532 nanometer wave. Now, to me, I don't know what that efficiency means in the sense of, why they didn't choose, why they choose 532 and not something else. Okay, but it's a good thing to explore if you want to explore that. So here you can see here on the bottom, we have the ICET2 orbit. That's at 88 degrees north and south. And then we have the 51.6 degrees north and south for the GEDI orbit. So with a combination of ICET2, GEDI, and the GLOBE tree height data, we have a very robust amount of data in the database for GLOBE and in the NASA database to use this information. It's really, really amazing to have this amount of data. And you can read more about the ICET2 satellite soon. Okay. Now, I want to show you this because this shows you how ICET2 works. This is one of my favorite videos. I've shown this a couple years ago, but it's all about the lasers of ICET2. And this is an interesting one because it shows you how precise ICET2 has to be in order to take these measurements. And of course, it's going to focus on, it's going to focus on climate. It's going to focus on the ice. But think of it this way: when you see it when they talk about measuring the ice, the same thing is done. It's done the same way when it's looking at trees. Okay.
The ATLAS instrument on the ICESat-2 satellite measures elevation by timing the flight of laser light pulses that leave the satellite, bounce off the surface, and return to ATLAS. The speed of light is very fast, and so a regular stopwatch would give us too wide a range of time, a big margin of error. The timing has to be ultra precise, less than 1 billionth of a second, in order to measure the height of the surface within just a few centimeters.
I'm Phil Lors. I'm Deputy Instrument System Engineer on the ATLAS instrument on the ICESat-2 mission. Calculating the elevation of the ice is all about time of flight. It's time of flight of the photon from the laser down to the surface of the ice and back. So what we are doing is creating time tags of the transmit when the laser fires and time tags of the receipt of the photon. So it all starts with the transmitter. When the laser fires, it puts out billions and billions of photons. We pick off a little bit of that and we send it to a detector and we produce a start pulse. And that is the start of our timing system. The spacecraft sends us a position and attitude message every second that tells us where we are in the orbit. From that, we calculate where we think the spots are on the ground. We have a rough database of the whole Earth with elevation as it travels up and down mountains and down into valleys and over ice sheets. For each spot, we calculate where we think the surface is, and we open up a range window. For every photon that's received in that range window, we produce a time tag. Now, the sun produces a lot of green photons too, many more than our laser does. So our laser produces billions and billions of photons with every shot. If you add the noise in there, you won't be able to tell the sun's photons from the laser photons. So if you just took one shot, the one laser photon would be lost in the noise. But if you take 200 shots, now finally you have enough surface signal coming out of the noise that flight software on board can pick out this is noise and this is the signal from the surface. Once we downlink the photon time tags from the receiver and the transmitter, and we have the range windows, we put those all together, you have the transmit time tags, you have the time until the range window opened, you have the receive time tags in the range window. You calculate all that put together, gives you the time of flight of a photon, which ultimately gives you the distance between the spacecraft and the ground. So if you know where the spacecraft is, you know the time of flight, you know the distance to the ground, now you have the elevation of the ice.
Or trees.
Technology that can measure elevation adds a third dimension to how we map our Earth and allows us to study change across the poles and beyond.
All right. So that was ISAT 2, and I'm going to briefly talk about GEDI, and then I will pass it over to Peter Nelson to talk about Landsat series of satellites, and then the upcoming Landsat Next mission coming up in about, I think it's, what is it, about 5.5 years maybe until that launch. So GEDI, as I mentioned, GEDI is an instrument on the International Space Station, and its focus is just looking at the height of tree canopies in that specific range of latitudes, as I mentioned earlier. And what you can see here, this is actually GEDI data that has come in, that this is mapping that scientists have done using the GEDI data. You can see here, this is a global map on the left side, and you're seeing all these tree heights across the planet. And on the right side, you're seeing it just as in part of the United States. It's off the west coast of the United States. So right here, Peter Falcon and Peter Nelson are being covered by trees in this, because once again, Peter Falcon is in California right now, and Peter Nelson is Oregon. So you can see here, this is really, really cool in how we can create these global, how the scientists are able to take the data and visualize it to the point where they can figure out how we can get these really cool global maps. And it's all being done through laser altimeter, that single, part of the spectrum, looking at a single spectral band, looking at that, the red, remember this was the red lasers and the ISAT 2 was the green lasers. So just one of the most interesting things. Well, one thing I want to mention also about GEDI is that GEDI was, as I mentioned earlier, that it was put up in December of 2018, and it was in utilization until one part of last year. And then we actually had to have the astronauts take it out and put it in storage because another part of the U.S. Department of Defense needed to put some instrumentation on the ISS, so we had to pull that back. And then they're done with that. So GEDI is back working again. It was reinstalled by the astronauts on the space station, and it is firing again and firing those red lasers and taking observations. So here's just a quick example I like to show about how this data looks when the scientists are looking at specific regions across the Earth. And this happens to be from, both of these are from ISAT 2. And here you're looking at the Bahamas, and you can see here in the Bahamas, we have this really thick green line. This is the ocean surface in the Bahamas. And then the squiggly lines on the bottom is bathymetry, or the ocean floor. What's so cool about this is this area of the Bahamas, it's the water is very shallow and clear and still. So the laser photons from ISAT 2 are able to bounce through the water, travel through the water, and hit the ocean floor and then bounce back to the satellite. On the bottom, we have Sequoia National Park in California, where we have You can see here, ISAT-2 has measured the terrain or that elevation. You can see you have some hills and valleys, peaks and valleys. But what I want to draw your attention to are these green spikes. Those are the trees. And those yellow dots you're seeing, those are the laser photons that hit that where we get the measurements from. So, but all those the green that look like trees, that's what they are. They are trees. So this is an area in Sequoia where we showcase because, as you know, some of the largest trees on the planet grow in Sequoia National Park in California. So just wanted to highlight that as well. So, all right, I'm going to back out of this because this is something for later on, something we want to showcase, and I'm going to stop sharing. And Peter Nelson, if you would like to talk a little bit about Landsat, I will pass it over to you.
Oh my gosh, Brian, of course I want to talk about something like Landsat. So I'm really definitely excited, to be here today during our webinar. And I'd like to start off, one, celebrating Earth Observation Day, which is kind of an informal day that many of us have started celebrating over the last 10, 15 years. And so, and it's all about just going out and making those observations, appreciating the world around us. And, in part that goes to this very notion of what we're living in, right? And we've talked about this in the past webinars. If you're part of the GLOBE community, Landsat was foundational to what started our measurements, why we are motivated to make measurements on the ground, because we have the satellite the satellite perspective. And so I just kind of want to highlight that we have luckily been inherited 50 years of satellite imagery. And as Brian mentioned, we're right now, other people, not me, are preparing our future. And they are preparing this next satellite, Landsat Next. And so, the whole reason for this is to have a long-term record of Earth. So as you think about different projects, or even, how long does it take for a tree to be the size that you're measuring today? That might be embedded within these measurements that have been made by usually other people or other satellites at a different moment in time. And the great thing is, for me anyway, a lot of measurements are being made when I wasn't thinking about the land cover around me, or I wasn't thinking about the world around me. I wasn't in some of these different places, but these satellites are there, and they're able to provide us that perspective, both what it looks like today, but also what it looked like historically. So this is a great tool to complement what we have in the GLOBE database. And like I said, we'll get into that. But again, most of us aren't continuously taking measurements. But these satellites are our companions and our secret weapon to be able to give us this insight. I want to start with what is this? Brian, showed his view of the Earth, those graphs, a two-dimensional sort of shape of things. But here is Landsat's perspective. And this is a wonderful tool that I think is great to help us understand, one, what it means to move along with the satellite. The unique perspective that looking straight down from Earth provides to us. I wanted to highlight, though, this is just straight off of the satellite. So it hasn't been processed. It actually has atmosphere in it. And so this is, kind of an interesting view of what Canada actually looks like. And I find this, the difference between our map that's indicating where we are, which is showing actually snow, versus what is actually on the ground. And so, to me, the exciting piece of what Landsat provides to us is this component of what it looks like on Earth right now. And what's nice about this particular website is you can go through and you can find different places on Earth and get a relatively recent view of things. And before we jump off and answer the question of what are we looking at, what I want to do is show you when you first start these, it actually highlights sometimes, if you choose the right place, there it is, what is actually happening. Unlike what Brian showed to us, we're making multi-spectral measurements. And we can actually see that at the very top of our strips, where you actually can see the individual bands of blue, green, red, light, and how those individual measurements come together to give us a color image. And that's what it allows us to see things as true color. Here we can actually kind of see the way those images overlap. And if we keep going, you'll see the colors that we're so used to seeing, which again is made up of at least 3 measurements coming from from space and those sensors. And so here we can see in this location, it's white. And again, you know, one of the powers of these satellites is this is what it looks like to us humans. We can actually start using some of these different measurements, you know, because we're not making a single measurement like Brian was highlighting. We're actually making anywhere from 7 to 250. That is why we call it multi-spectral, is there's many spectral measurements here. And so, you know, you do actually have to learn a little bit about what these categories are, like color infrared. Okay, well, that looks white again, right? Why does this one look blue? You know, and that all gets into some of the specifics that we can go into. But I want to highlight how, you know, vegetation analysis, well, that should tell you something about photosynthesis, right? You can use those as indicators to start the conversation. Again, why would we have these colors? And this is what scientists like me like to spend our time doing, is manipulating all of these measurements together to come up with something that is a color or something similar to what we're seeing. And so we'll let that just kind of go. But again, I find this to be a great hook of what are we seeing? Why are we seeing what we are? And getting into that satellite perspective. And again, to help all of us understand multi-spectral, here is you know, our tour of the electromagnetic spectrum. And this is what we're doing with our digital camera. We're recording red light, R, green light, G, and blue light, B. And that allows us to create these color images that all of us are used to seeing on our mobile devices, right? You're actually measuring these 3 different wavelengths and the way that they're reflecting off of those surfaces. So all of us are used to working with multispectral imagery, actually, red, green, blue. The key with what we get from NASA and some other sensors, like we've highlighted, like Stella or even some of the thermal imagery, is we then are, again, making measurements, but just in specific wavelengths or different wavelengths that are maybe outside of our natural color, what our eyes see. And this is what allows us to start doing things that we call false color images. And that's what we were doing, where, again, we just choose some of our other measurements that these sensors can make, and we can combine them together, and you start getting these colors that are not the ones that we're used to seeing. Again, I'm not used to seeing a cloud in cyan or that blue-green color or a purple color. And this is where we have to go back and look at what is actually getting measured and maybe why does it look the way that it does? Is it bright or is it dark in whatever we're measuring, red, green, or blue light, or something outside of what we can actually see? And so, to me, this ends up going into the investigation, right? Why do we have the colors? Why does it look the way that it does? I'm not used to seeing that. And what is going on there is the investigation that many of us are looking to understand when we put these colors together. Again, we're very limited because our computer monitors only allow us to see a combination of 3 colors or 3 bands or 3 measurements at a time. And so that's why you will see only 3 different wavelengths or measurements going together. So we have to make a decision about what we want to see. And again, this is where scientists have given us a way of understanding that. Now, what Brian was showing us is ISAT-2 is measuring this green light. It's only measuring that green light. GEDI, that instrument, is measuring in the red light. So we already have something that is complementary to what we're measuring on the ground. And so with the GEDI, how does that relate to the red colors that you're measuring in a location? On the ground, how does those ISAT-2 photons and measurements respond to that intensity of green that you're seeing in your ground measurements? And then this blue is, again, something that's used by photosynthesis. And so you'll find that when you look at just the blue light, you'll see that that is actually getting absorbed and it's darker in those areas where there's vegetation and photosynthesis. But it reflects off of water. And so, and that's why water tends to be sort of blue to us. And so again, just starting to think about and look at the fact that you've made 3 measurements with every single one of your land cover photos or with your photos on the ground or of that tree, to me gets really exciting. And again, when we start thinking about the color of the bark, like what's behind me, we're actually looking at the combination of these 3 measurements together. And that's where it gets it can get very, very complex, or you can separate them out like what Brian has shown us and just focus on one of these wavelengths and one of these measurements. So, we have resources that will help us go through this. But I want to highlight that, again, like, it's really confusing if somebody just shows you a color image and they don't tell you what was actually being measured. Okay, so we should always be asking each other, what are those wavelengths that are measured and presented here, even with this ground image behind me? It is my blue, green, and red wavelengths. And we should all highlight that to each other and talk to each other in those, because that's really important information that gives us context to understand what I'm actually presenting behind me. Again, like, this is it's a really interesting, fascinating topic, and it is really important to understand, because when you start looking at satellite data out there, you have to understand some of the terminology. Again, natural color is what we're used to seeing, what you would record on your mobile device. Color infrared, okay, what the heck is that? We have some indications by the name, but that's something that we need to go and explore before we can really understand what we're seeing. False color, again, that's actually giving us some indication that we're dealing with measurements that are maybe not what we're used to seeing, the natural color. Enhanced here, highlighted for vegetation. Again, what that looks like, why that looks that way, we need to go and investigate. Again, and by putting together some other combinations, we can even highlight the urban part of our landscapes. And what I mean by that is the non-vegetated areas in particular, pavement and other pieces like that. Or you can just look at that single measurement of green light, or you can put together your own combination. And with Landsat, it's relatively simple. we have 6 spectral bands that we've measured. Our blue, green, red, near infrared, some shortwave infrared, and all of that's described in some of these resources we provide. There's 144 different ways that you can put together those different measurements that have been made. So which ones do you choose? Well, start off with the ones that are presented as drop downs, explore those. But again, it's really interesting to just see the colors that are created and then go out and investigate them. Why might they be that way? And so this, is a great place where it's really important to be thinking about your cloud cover, because that is one of those things with natural colors. Even those measurements that Brian was highlighting, they can be reflected by clouds. They can be influenced by that atmosphere. So sometimes it's really important to filter for those clouds to be able to get rid of them so that you can see that. So this is, again, a connection between why we ask you to do cloud observations with your ground measurements. So you can go through and see that here on this particular website. You can also explore the particular sensors and their timelines. And again, part of the reason why we have our better sensors today is because of what we learned from these past research experiences. The other thing that it can be really helpful that we've talked about here, and we're in the middle of this, is that we're not just always concerned about our single date. We actually want to think about the seasonality, right? We're actually talking about, the fall time right now and our leaf off conditions. So when is that, right? And so our date ranges are an important way that we start thinking about our satellite data, our multispectral satellite data. Okay, so this I wanted to highlight, this as a particular tool that allows you to get in and start just looking at and starting to work with this satellite data and being able to, as you keep zooming in, you'll start to see how all of this imagery, this multispectral imagery, is organized and what you can find at different locations. I could keep going on with this one for a really long time, but I encourage you to go in and explore this. Exploring a digital space for these things is a skill, and none of us have really the answers. And so it's fun. It's a fun activity to actually do together and see what you can create. You can do time lapses and other ways of putting our data together based on time ranges. So again, you'll find Landsat data all over the world and all over in a lot of different places. So I want you to again, just get in there and start recognizing there's different ways of seeing these depending on who you decide to interact with. But notice that there's natural colors, there's different ways of combining these spectral measurements, these sunlight measurements together to be able to identify and see different features. And part of our fun is actually playing with these colors and asking the question, what the heck is this cyan color? And using the context of place, of maps, and even what we know about what is being measured to fully understand the landscape that we're looking at. So, again, I just want to really highlight that our images that we're working with are multispectral images. We had to do a data reduction to only choose 3, to be able to make this color image. So we would love to see students take this next step and go beyond just that one measurement of green light with ISAT-2 or red light with GEDI, and start thinking about what it can be measured and how that can tell us about those the health of our landscapes, the features on our landscapes, because again, I'll go back and end here. Hopefully it'll line up. Landsat Next is just one of the satellites that is going to be up to be making spectral measurements like this. There's a whole lot of satellites that are going to be making even more measurements beyond R7 or what Landsat Next plans on doing. 25 of those spectral measurements to better understand, again, the health and some of the properties that we're measuring with our GLOBE program. So get prepared. You know, this is the data that we need to start thinking about. What are the measurements that we'll get from this satellite or these other ones that we want to highlight for you that are coming online to help us get understandings of the world around us in a way that our natural colors sometimes don't fully reveal. Hey, Brian. Do we have another satellite or mission that we want to talk about?
We do, and Peter, I'm going to pass it over to Peter Falcon, and he is familiar with the NISAR mission, which is going to be the focus of our featured presenter at next month's webinar. So let me pass it to you, Peter.
Thanks, Brian. And also, I put down in the chat box, if there's any questions for Peter, please feel free to put them in the chat box. I know he monitors them. He'll be able to answer any questions you may have about the electromagnetic spectrum and about his presentation. We also included a resource there, the electromagnetic spectrum booklet, where Brian grabbed that great graphics from. There's more information there, so if you want to continue reading about that, feel free to download that. It's free. So with that, I wanted to talk to you a little bit about the NISAR mission, which is going to be a mission we're going to be highlighting next month with Dr. Erica Podest. She is a JPL scientist, a NASA scientist, and she is the wetland science lead. So she'll be mostly talking about the wetland application about NISAR. What many people don't realize, many of the NASA satellites first start off as instruments onboard airborne campaigns. So we have quite a few different airborne campaigns where we put instruments on board, fly them around our planet, pilot that new technology, make sure it's working properly, make sure it's working and doing what we say it's working, or what we think it's going to be doing. And when that technology is working properly, we can then go to NASA headquarters, propose for a bit more money, actually a lot more money, and put a larger version of that instrument on board a satellite. And now we can get a global perspective of what we're studying. And that is basically the way instruments like ISAT-2 started with IceBridge, and NISAR with an instrument called a UAVSAR, which was on board an airplane. So because of the success of the UAVSAR mission on board this airplane, we now will have, knock on wood, NISAR, which will be launching early next year. And NISAR, the running joke is we call it a nice satellite. We call it NISAR because it's a nice satellite, but really what it stands for is NASA, Israel, Synthetic Aperture Radar. So this is a joint collaboration with Israel, which is the country of India's version of NASA, their space program. This allows us to save the cost to partner, have international collaboration, most importantly, but also save cost on the development of the different instruments. Also save costs and then share the data. So this is a great partnership for us. And as I mentioned, we're going to be launching early next year. NISAR is really like the Swiss Army knife of satellites. Each one is very unique. Each one can do something very special. NISAR can do a lot of different things, much like a Swiss Army knife. So it has a lot of different science applications, has a lot of societal benefits and different aspects of what we're studying with our planet. So as I mentioned, I don't want to steal too much of Dr. Podest's science applications that she'll be talking about next month. But what I will do is share some of the links from the NISAR mission so you can kind of get an understanding of what it's like and hopefully come prepared with some questions for Dr. Podest. Also, I will share some of the societal benefit story maps that we put together so you can kind of learn about the impact of this mission on our daily lives. For example, NISAR will have cryosphere applications. It's going to be studying glaciers. It's going to be studying ice sheets melt, glacier melt, having applications on sea level rise as well, the impact that's going to have on us, people who live near the coast. It's going to have applications with biomass, understanding the biosphere, understanding deformation as well. Agriculture, it's going to be able to understand areas that are prone for planting agriculture, as well as water applications, subsidence, groundwater, as well as ocean and sea level rise. It can understand natural disasters as well, and things like volcanoes, earthquake faults. What makes NISAR very unique is it can make measurements that are a difference up to about 1 centimeter. So while it's in space, it's going to be about roughly 750 kilometers in space. It has 2 instruments called, both of them are radars, an S-band, which is, I believe, 9 centimeters, and then an L-band, which is going to be 24 centimeters. And it has a synthetic aperture radar, which is going to be about 3 to 10 meters, depending on which mode it's going to be in, which is going to give us very high resolution of what's going on with our planet. And as it goes over the same spot every 12 days, when it goes over an earthquake fault, it can actually see the displacement of that fault. So we can see it getting bigger and bigger each time we go over it. And then with volcanoes, we can see as the volcano is about to erupt, kind of the movement of the volcano. So we can see that from space, roughly about 750 kilometers in space. So it's going to do a lot of great stuff for us. As I mentioned, cryosphere, ocean, land, subsidence, agriculture. So a lot of different things. And as I mentioned, when Dr. Podest presents next month, she'll be talking about the wetland application for NISAR. So this is something we're very excited to have. As I mentioned, it's going to be launching sometime early next year. We don't have an exact date, but we're going to get some great data, and we're really looking forward to that and sharing that with everyone. So please stay tuned, and I will go ahead and share some of the different links that we do have so you can continue reading about the NISAR mission. And if you have any, yeah, feel free to put them in the chat box.
All right. Thank you, Peter. Yeah, that's great. Yeah, we're excited to hear from Dr. Erica Podest next month. One thing I should mention, though, those of you who have been with the campaign for a while, you may remember that she gave a presentation in the first couple years of the campaign, and it was all about trees. I believe it was the lungs of the earth that she presented on. And if you were part of our SMAP student research campaign that we did years ago, she was an integral part of that as well, because she was a SMAP mission scientist looking at soil moisture specifically. So she's a great asset to NASA and the GLOBE program. She knows both groups very well. So we're super excited to have her as part of it next month. So, and thank you for Peter for talking to her and having her on. It's either going to be, I believe, but either November 12th or the 19th. I think you're confirming with her now. I think I can't remember offhand what date we thought about, but yeah. So we'll get that information out as soon as we get that specific date set with Dr. Podest.
Also, to note with Erica, as I know her, she is from Panama. She's a native Spanish speaker. So for those from Latin America, Central America, feel free to ask your questions in Spanish. She will answer them and give you a much better answer than we could in Spanish. So this is a great time to kind of use that resource. That is very good presenter, and very patient with their time.
Excellent. Thank you, Peter. Yeah, she's one of the best when it comes to presenting and getting talking about our information.
Before we head off to our feature highlight, Brian, I wanted to just bring up the Tour of the Electromagnetic Spectrum book. Page 12 is what Peter was talking about in terms of what these radar missions are actually measuring. And so you can see these funny acronyms at the top here, and sort of he was talking about L-band and things like that. So I find this to be really a good starting point to start thinking about radar data, which is similar but also different than the multispectral data that I was highlighting. So again, we wanted to really highlight the kind of 3 different ways that we're making measurements of trees around the globe and their environment that they're in. So again, as you start hearing about S-band or X-band or K-band, you know, this is a good reference to see what they are, because they're not in alphabetical order. All right, Brian.
All right. Thank you, Peter. I'm just looking to see. I don't see any questions yet. Everyone's super shy today, unfortunately. A couple of people had to leave at the top of the hour. So, all right. So, and we'll definitely have to end this at the half hour, because some of us have some other things going on with the NARM right after this. But so with that said, let me go ahead back and share my screen again and stop talking about that. Okay. Oops, sorry, it went too far. There we go. Does that look okay, Peter? Either Peter?
I don't see anything.
Weird. Share. Strange.
Yeah, just go in presenter mode and you should be good.
How about now? Good.
Perfect. Mm-hmm.
All right, cool. Yeah, that was odd. That's Zoom for you though. All right, so as I mentioned earlier on in the webinar, you know, with this campaign, since we are aligning to the 2025 IVSS 30 years of GLOBE data, looking at 30 years of the past, present, and future, we are going to have that kind of flavor looking at the past, present, and future. And I know Peter will talk about this image a little bit more, but John Moore, who's on today with us again, he sent this picture to us in the last few minutes, and this is what it looked like this morning, one of the trails at Palmyra Cove Nature Park. So yeah, so that's kind of what we're looking at right now. That's what that's the greenness that you're looking at right now in this picture. And then, but I wanted to also share that, you know, we can look at these areas. You know, we can go out here and this one and take tree height measurements. We can do land cover observations. We can also do comparisons like this using ISAT2's data, open altimetry. We have what you're looking at here on the left side. This is basically all the area of Palmyra Cove. You can see the bridge there, and if you see the building with the white roof right there near the bridge, okay, that's the Palmyra Cove Nature Park building, the Institute for Earth Observations. That is part of it. And then on the right side, what you're seeing here, these are the photons that ISAT2, when ISAT2 flew over, dropped on this location. And these are all individual photons. And I'm pointing to one there because there's one here that we were focusing on when we were at Palmyra Cove. And I say we, this is part of our ISAT2 team working with John Moore and some visiting teacher and her students, as well as, you know, there was the NARM was there earlier this year. So we're looking at this this graphic here, and I'm highlighting this one photon. And I want to show you something interesting about this photon, is that when we were there, and John, correct me if I'm wrong, if you're still on, that I believe it was February of 23, we were there, and we went out and took observations, specifically measured these trees that were right on the edge of this trail. And then we came back for I was there for ISAT2, was doing some ISAT2 stuff. We set up an exhibit there, an altimeter exhibit for ISAT2. But then also we were back there for that NARM earlier this year in March, I think it was.
That's correct, Mark.
Yes, and we went out there, and those trees right there are no longer there. Was it something, John, with the Army Corps of Engineers was doing some work there and had to take some trees down around the coast of the river?
Yes, that's correct. Yep.
Yeah. Okay. That's what I thought. Yeah, because we went out there to measure these trees again, and these trees weren't there, unfortunately. You know, just about a year later. So, but we do have it in the database. When the tree was there, we have observations of it, and they are in ISAT2. So what you're looking at here is we're looking at how ISAT2 has measured this tree and these trees. And when I mention this, I say trees because, as you've heard before, when the laser photon hits the ground, okay, when that energy from the photon hits the ground, it's about a 13-meter diameter footprint. So what that means is that when ISAT2 drops that photon and it hits the top of trees, the height that's returned, what you see here in the graph where it says canopy height 14.34818 meters, okay? When you see that, that is the average of all the treetops that ISAT-2 hit in that 13-meter diameter footprint. Sometimes, on a rare occasion, it'll hit an individual tree, one tree, if it's an isolated tree, but that's super rare. You get most of it like this, where there's multiple trees in that area. And when we were doing it here, this was on the edge of this. You can see it was on the edge of this trail. So therefore, when we went out there, there were about 3 trees. There are 3 trees that we figured that ISAT-2 landed on. So we took observations of these 3 trees, okay? So then I just wanted to show you this. Like, ISAT-2 has covered this area very well. And we like this area of Palmyra Cove because great land cover and great amount of trees here. And I just want to showcase this as an example of one of the things that, you know, we can do. We can do the ground-based observations, you know, using things like the GLOBE observer and handheld clinometers through GLOBE. But then we can also use that single spectral band, that green laser light from ISAT-2 and even GEDI. I didn't see any specific GEDI in the database at this, you know, at this exact spot, like where ISAT-2 hit, but close by. So then once again, there's another one we were focusing on as well. And you can see here how the ISAT-2 band, how the ISAT-2 orbit runs over, forming this band of photons. And the reason why they're paired like this is basically one side is the weak photon, one is the strong photon. And we get a lot of the better data from the strong photon, but the weak photon is there because we want to be able to match up some of these measurements. And then I just want to show you this. This is something that we get off Open Altimetry, and I'll put the link on there. And, you know, we'll be talking more and more about this, but I should say, you know, this data here is not present data. This is past data from the last, you know, over the last 2 years. Okay, we've gotten data like this over 2 years. Now, ISAT-2 returns to the same spot every 91 days, so there's going to be multiple observations of these trees that you're able to look at. And that's one of the reasons why we say about comparing data to ISAT-2, even though it's not an exact science, and we're still working on the idea of getting a tree height satellite match with a GLOBE observer, okay, because of the way the photons are measuring the height. We're getting just that photon footprint, which is a lot different than some of the other satellite data and how we receive that data, like we do like we get for like clouds and things like that on the GLOBE observer. So yeah, so I just want to showcase that a little bit because we've done some really cool work there. And thank you, John, for sending that information about the present. John, is there anything you want to mention about, like, you know, and I know for those of you who have given a who have been here for a while, John gave a presentation a couple of years ago at our Trees Campaign webinar talking all about the forested area in that location.
Yeah, I will just say a couple of things. So for the other participants to understand why I'm working with the trees, and in particular with Peter on the latest mission here, is we're looking at change over time. That's kind of the ultimate theme. And one thing unique about the Palmyra Cove, you may have noticed in the last picture, it's a green area. It's about 250 acres. But we're 7 miles north on the Delaware River from Philadelphia, Pennsylvania. So it's a very large city in the United States. And this is one of the few remaining natural areas. And it changes all the time. Brian mentioned about the trees changing because part of that area is a dredge retention basis for the Army Corps of Engineers. So every couple of years they dredged, they have to do dredging operations in the Delaware. And all that land, as a matter of fact, as we go back and looked at it over time, wasn't even there. That's dredge. A lot of that, what you saw in the opening picture, is built on dredge deposits from years ago. So a couple of weeks ago, when Peter and I were talking, we looked at that and kind of do the investigations of how things change, and then fast forward that for all of us to look how our locations change. So I'm a little bit older probably than most of you, so I could talk to Peter about what it was like when I was in school and compared to what it is now in New Jersey, where I live, the amount of development that has happened. So as an environmentalist, it's important to see what was and what is, and then use that data to predict what will be, or steps that we need to take to protect either forestry resources or water resources. So that's just kind of Reader Digest version of why we're doing that work here.
That's great. Thank you, John. Let me pass it back over to Peter now, because I know Peter has, like John mentioned, been working with John a lot, and he knows the area very well.
Yeah, I appreciate that, Brian. And I think one of the things that we're wanting to demonstrate here is just the amount of information. And one of the things that I kind of want to highlight is that images are just images. And it's just like a satellite image. And you can look at it, you can analyze the colors, and those colors might mean something. And so, luckily I know a little bit of something about, the ecology of the area. I've spent at least a little bit of time, so I have some knowledge. But we can see that there's some orange colors that are showing up in the midst of our green. Again, what we're seeing is that reflectance of light, that photosynthesis. So, that's telling us something about the process of those leaves and what they're going through. And so, we can use these photos as just measurements by themselves. And this is, kind of that first piece of, you go out, you do some, you use your phone to make some spectral measurements, and that's an easy way to track these color changes over time. And also, what's happening. I actually see right here, it looks like a tree trunk has fallen over, and so I see evidence of change right here, that may not be the main focus that John took of this photo. In fact, he was probably looking at the color change, the leaf color change. But because I have a different lens sometimes, I see, this evidence of past landscapes here. So, these photos have a lot of different values. And again, it's just exactly the same type of remote sensing as scientists are doing from above. But I want to highlight that when we go here and actually put them onto a map, or into our database here on the GLOBE site, they start to take on a little bit different meaning, right? And in fact, knowing which direction we're pointing in this photo starts to help us to know how that compares to the satellite imagery. Part of the reason why what we're measuring with all of these different instruments that we've talked about is actually this vertical structure of this forest. This doesn't just happen in 1 year. This takes many years for these trees to grow up and obstruct our ability to make a cloud observation. And so, so just recognize that you're out there, and you're, by using Globe Observer, you are actually recording how that place changes over time. And I like this because, John and I, or various other people of us, can have this conversation about what does this look like at this moment in time. But again, it doesn't have value by itself. It only really starts to take on a lot of meaning and a lot of value when it's put into this database. So, we're sort of going down on time, but I want to let's zoom in here. And one thing that I'd like people to do, because I think it's a fun little activity, is go in and just look at the imagery that is available, say, in the last month. Right. And one thing that I love about this viz system is that you can go in looking at the trees or the land cover, and you can start to see, well, the different colors, the different landscapes that are out there. So right now we're talking about phenology. How green is your pixel? Is really the big question that we're after. So again, I want to encourage you to go in and change your base map. Go to these 3 dots, and actually pull up satellite data like this recent view of what it looks like from above. That's really helpful because, again, if you're underneath any of these white clouds, you will not you will not, the satellites will not be recording what you're seeing. And again, here you notice true color. So I reviewed that earlier. So the colors that we see in this satellite image should align with what we see on the ground. Okay, but please, dive into some of these other ones. This chlorophyll A base map really allows us to, again, if we zoom in, it could potentially reveal that amount of photosynthesis that's happening in an area, or how much precipitation might be in that area. So, one of the things as we zoom in on, the area that we're focusing in on, right, is imagery can really give us context to the map or layers underneath, which might be very static. And I want to bring this in because here we're really using OpenStreetMap data. And here, if we look at this, we can see the Cove Trail, we can see the Beaver Pond, we can see a past observation that has come in. I really encourage you, because you're supposed to use a comparison to something in the GLOBE database. Well, photos are one of those. So dive in and see what an area looked like based on just these photos, and can you interpret them? Again, when I start looking at a photo like this, I can see that it's green. There's some yellow starting to appear on the leaves, right? So we're starting to have some leaf color change. But I'll highlight again, my eye goes right to over here where these big downed trees, this carbon that is now stored in this environment that is there until, as John says, somebody comes along and decides that this is a place that we need to store water, or we need to change this. So there's a lot of evidence here. I'm going to, end our little piece here with one of our other friendly tools, because I want to really stress that depending on what map or how you interact with the satellite imagery or the data that comes from the satellite imagery, hey, we actually have on this Google map, they're telling us that there's a dredge retention basin. And what is available to all of us in the United States, I'm showing this landscape change monitoring system that actually is showing us that, it looks like there's been some possibility of large timber harvest, small timber harvest going on in that area. And so we can actually see this dredge retention basin is labeled as having large timber harvest, large trees removed. Well, this is now a hypothesis that, hey, John, you can send people out, get us some photos of that location like you've done. And that helps us to start pulling together what we're seeing on the ground with these long-term changes that are, again, recorded in our satellite data. So, we want to highlight this, maybe a little bit more in depth even than what we've been able to do with John's site here. But you can see that the intensity or the year of change is available to us. And so we can actually start looking at the history of your location. And as we can see John doing right now, going, well, is that true? Oh, yeah. Okay. We can maybe see some areas where the beavers might have had some impact. And so it's not always people making changes out there. There's wildlife, there's other reason for these changes. And we really wanted to highlight how exciting it is to get to know an area and talk to somebody who has that long history, and even, make use of our ground photos that help us to understand what an area looks like today, or in this case, at when there's leaf off conditions, and we can actually see further. And so dive into this data, share with us what you're interested in doing, because as you can see, different times of year will reveal the different relationships of the environment around us, the cloud cover, and that all relates back to our satellite imagery that we can see and what that satellite is going to record in this location. So John, thanks for letting us highlight, the difference between what might be out there in your area and what you're bringing to us in terms of the GLOBE database and keeping us on track with today. This is what it looks like. And I love the fact that we have data from today in this database. So join us on this Earth Observation Day. Go out, make us some observations, show us how green your pixels are, and we will continue to highlight what it looks like beyond the natural color view, because that's really what NASA is doing, is focusing beyond the natural color into the health of our environment like this. So thanks for our Trees Around the Globe student research campaign team. And I am excited to, kick off and see where people actually go this year with the data that we're able to provide to you.
Same here, Peter. Brian had to step off. He is going to do another presentation for the NARM meeting, which is going to start in a few minutes. So he just said a quick thank you for everyone and in the comments, and I think he stepped away. So yeah, if there's any more questions for Peter, please once again either unmute, ask him, or put them in the chat. We can address them. But if there isn't, then I think we can probably wrap up because I know I have to get to another meeting as well, and I know you're always busy, Peter, with class and everything.
And everybody else here too, right?
Yes, exactly. So we want to encourage you to, once again, check out the recording if you missed anything. It's going to be posted in the next couple of days. Brian usually does that fairly quickly. And then once again, next month, please come back and hear about Erica, the presentation on NISAR, and the other keynote speakers that we have. I know Peter always presents. He always does a great job. So once again, we just want to encourage you, say once again, thank you for joining us today, and encourage you to join us next month.
Yeah. And I want to highlight, for those of you who are outside of the United States and may not be on that map that we were showing earlier, I put into the chat something that I've highlighted in the past called earthmap.org. This provides global data sets where you can explore kind of the same sort of things that I was highlighting earlier. And, to the piece of, I don't know how to interpret this. Well, that's what our team is here for. So, we want to help everybody understand this data. And so that interpretation and understanding the data is the science process. So let us know how we can help with that. And we'd be glad to display it and walk through how we interpret that and hopefully bring you into the conversation like we've been able to do with John here to give us at least some insights into why are those pixels green? What is the vegetation that's actually there? Because that's just a sample of the world, and you help us to really understand that sample that is there. So, let's go out and see what kind of trees are out there today and this year. So thanks so much for joining us today.
Yes, thank you, everyone. Have a good day.